Let's talk about how to convert from one base to another, primarily in Python. So we're going to look at decimal to binary conversion, look at a couple of different methods, and then a couple of methods that go in the other direction. So let's convert the number 317 to binary. So one method would be to repeatedly remove the largest power of 2 from the value and keep going until we get down to 0 and have no powers of 2 left in the total. So here we are working strictly with decimal integers, not worrying about any fractional portions. We could deal with the fractional in the same way, but in these examples we're just going to deal with integers. Okay, so the largest power of 2 in 317 is 256. And so in our leftmost bit, we don't know how many bits we're going to have at this point. We don't really care. We're going to say that is going to correspond to 2 to the 8th power, so the 256 position. From that, we can tell how many bits we're going to need, but we don't have to worry about that as we progress. So when we subtract the 256, we're left with 61. So from the 256 position that we have the 1 in, the next position to the right is 128, so there are no 128s, we put a 0 there. The next bit after that corresponds to the 64 position, and so there's no value there. We record a 0 in that bit as well. The next position is 32, which corresponds to the largest power of 2 that is not more than 61. So we're going to record a 1 in that position. Remove the 32 that we have now recorded from the 61, we're left with 29. The next power of 2 that's not larger than 29 is 16, so that's the very next position. We're going to record a 1 in that bit. Remove the 16, we're down to 13, and that leaves an 8 as the largest power of 2 in there, so we record a 1 in the following bit, which again corresponds to the 8 position. Remove that, and we have 5. So the largest power of 2 is 4, so we're going to record a 1 in that spot. When we subtract the 4 from the 5, we're left with just 1. But the next position corresponds to the 2's place, so there is no 2 in 1, so we record a 0 in that bit. And then the final rightmost bit is the 1 that we had. So we subtract that 1, the process then ends. So this means that our value that we had recorded, we had a 1 in the leftmost bit, and then a couple of zeros, and then the 1s that we have, and so on, and then finally another 0 and a 1 at the end. And so this step-by-step gives a string that corresponds to the decimal number 317. So when we write something in binary, in this case, we're going to write it as a string, especially when we're working with these calculations in Python. We're going to record these pieces as a string and convert back and forth to numerical values as needed. Okay, so this approach, we start with the number and take away the pieces until we get down to 0, and recording in our binary string what the result was at the different steps. Okay, so if we want to do this in Python, we have to keep track of what we just did. What are we doing? We're saying what's the largest power of 2 that's there? Are we going to record a 0? Are we going to record a 1? All right, so one way to do this corresponds to using a bit of math from the math module. And so if we are going to create this function, let's say it's going to be the decimal to binary converter, and since this is our method 1, we'll add this _1 to the end of it. When we write a function, so we have the DEF, we're describing a function, it's called decimal to binary, and we have this parameter, which is number, that is going to live just inside the function, something we're going to pass a value to the function, and it will be called number inside that function. So we have the parameter number, and when we actually use the function, we will have an argument, so that'll be the actual number that we put into place, so like 317 if we write this and run this. So the next line here we have our docstring. This is a one-line docstring. We will see soon lots of examples of functions that have more complicated docstrings where we describe what all the parameters are, and we describe what any kind of issues with requirements and what the input exactly needs to look like and what the output is in this case. But this is a simple enough function that a single line works. We always start a docstring with 3 sets of double quotes and then end it with 3 sets of double quotes. We will see some slight variations on how we will work with multi-line docstrings, but for now, the single line docstring is, this first line is always an action sentence. It says what the function does. So what do? We're going to convert a positive integer, in this case, to a corresponding binary string. Now, in a lot of situations, we try to be very descriptive, but not too descriptive. We don't want something that's too long. We want it to fit in one short sentence. The full stop at the end, the period at the end, is necessary in the standard in terms of describing what a docstring needs to look like. And as we go on to other examples, we will see some other standard guidelines of what a docstring is supposed to look like. And then later we will see where docstrings show up and where you can see them, why we write docstrings and what the point is. But the idea in general is to make it very clear to someone who looks at your code what your function is supposed to do, what the input looks like, and what the output looks like. And so sometimes the person that's reading that code and trying to figure out what you were talking about is you at some point in future. When you're working on something, it makes sense. Oh, I'm going to do it this way, and here's what my input is, and here's what my output is. And then a long time later, you look back at it and you've forgotten what you were thinking. But if you wrote good docstrings at the time, you will remember what you're thinking. And other people can see your docstring if they were using your code. If we write we're going to write some different modules ourselves that have lots of functions in there, and so other people would be able to look at your code, look at those docstrings, and be able to understand your mindset, what you were thinking, how things work, what this function is supposed to do. You've noticed in using Python, if you're using, say, idle, that if you start to write a function, then pieces will pop up, and sometimes an explanation of what the function does will be there, and that comes partially from the docstring. If you use help, the help file also is created entirely from the docstrings. So we'll see this in more detail as we go forward. Okay, so what do we want to do with our decimal to binary conversion? We're thinking of the steps. We say we have this number, and we're going to find the largest power of 2 that goes into it, and then we're going to start to decrease that power of 2, or start to decrease that value by powers of 2, and keep track of, did you use that particular power of 2, or did you not use that particular power of 2? If you used it, you're going to put a 1 in the binary string, and if you didn't, you're going to put a 0 in as the bit in the binary string. So to find out the largest power of 2, we have a bit of maths here. The logarithm of a number will calculate the exponent that you need to raise, in this case 2. What power do you need to raise to 2 in order to get your number? Now, in the case of 317 that we saw in our example, that's a decimal value. and we want to know the integer number of the power that is the largest power. And so we're going to calculate this in terms of the int of that number. So int, the way int works is if we have a positive number, it's going to round down. It's going to round towards 0. If we had something that was a negative number and we apply int, that rounds, again, towards 0 as well. And so we talked about rounding and different kinds of rounding, and int is one that always rounds toward 0. But in this situation, we're going to have this number, whatever value we ultimately put in here, then we're going to use the math module's logarithm function to calculate this exponent, and then we're going to look at the whole number portion of that exponent. And this will be just the biggest power of 2. So this is the exponent itself, not like we just saw in the previous example, not the 256, but this would be the 8 that corresponds to the log base 2 of 317. Okay, so now we know the biggest power, and we want a place to record the bits as we calculate. So we're going to create an empty string here that we'll just call binary in this case. And so now what we want to do is, since we're working from left to right, we're starting with the highest exponent. So that's the t, that's the biggest power of 2 that shows up in the number. And then we want to work our way all the way to the far right, which is the ones position, or 2 to the 0th power. So remember that range has your start value, and then in this case we're going down, we're counting by -1, so we're going from t down to -1, but we don't include the last value. So whatever the highest exponent is, we're going to start there, and this range calculation will take us down to the 0th power. So start with t and go down to I at the end being 0. And so we're looking at this and we say, okay, we're on this particular power. If 2 to that power is less than or equal to the number, then that means that that value is going to be part of the number that we have. So that means that 2 to the I is less than or equal to the number. And so we're going to append that 1 to the end of binary. Now we know at the very first value, that value t, we are going to append the 1 because we calculated t and it corresponds to the biggest power. So we will have a 1 as the first entry. But then once we have recorded the 1, that means that we then need to remove 2 to that power from the number. So we're going to update the number by removing 2 to the I from that value. And then we'll do it again. And we keep doing this again and again. But if 2 to the I is not less than or equal to the number, so as we're working across, if we run into, after we've subtracted something from it and we run into a value that skips over a power of 2, then we're going to append a 0 to say that power of 2 doesn't show up in this particular number. And so as we're going from t down to 0 through 0, we're including 0 in this, from t inclusive to 0, we're checking, does that particular power show up in our value? And if so, we record the 1 and then subtract 2 to the I from that. And if that particular power of 2 is too big for what we have left, then we're going to skip over that one. We put a 0, we don't change the number, we go to the next I and keep working our way from left to right in the binary string in the calculation of, does this power of 2 show up in our total? Okay, so then what happens at the end? When we finish this values, when we finish going through all these powers, We are at 2 to the 0th power. We have recorded whether or not to include the 1 at the end, and we return the binary string that we have calculated. So if we have the ones place at the end or we don't have the ones place at the end, depends on what's happened up to that point. Is there a 1 there or is there a 0 there? This loop will calculate that, and at the end we return the string that corresponds to the number. So this version of this decimal to binary conversion does exactly what we did in the previous on the previous description in that example of going from 317 and writing it as a binary string. Now, there's other ways we could do this as well, converting this to binary. Another way to convert to binary is we keep track of what happens with repeated divisions by 2, and the remainder is an important task. So we want to divide the 317 by 2. Well, 317 is an odd number, so we get the whole number portion, and then we get the remainder. So 317 divided by 2 is 158 with a remainder of 1. So we're going to keep track of both values, the 158 and the remainder. So 317 divided by 2 is 158. The remainder is 1. We're going to repeat this process with the 158, and that gives us 79. At this time, because 158 was even, the remainder is 0, so we record those two pieces. Now we do this again with 79. We have 39 with a remainder of 1. 39, we carry that out. We had 19, so we do this again with 19. With 9, when we did 9 divided by 2, we get 4, but there's a remainder of 1. 4 divided by 2, that's 2 with a remainder of 0. 2 divided by 2 is 1 with a remainder of 0. And we go all the way until this final value becomes 0 itself. Now 1 divided by 2 is 0 with a remainder of 1. So at this point, we have done all of the dividing by 2 that we possibly can. So all the values of dividing by 2, the number of times we've done that, corresponds to the biggest power of 2, that's n 317. And we notice that we divided by 2 9 times, and so that corresponds to also the ones place, and so the number of divisions by 2 here corresponds to the biggest power of 2 being 2 to the 8th, or 256. Now when we look at these remainders, the remainders are the part that tell us what happened with the calculation. So the step-by-step dividing by 2, keeping track of the whole number portion and the remainder portion. To create the binary string, we're going to read that in reverse order, read that back up. And so our binary string will be 100111101, and that is the binary value that corresponds to the number 317. What does it correspond to? From left to right now, we have a 256 in there. There's a 32 and a 16 and an 8 and a 4 and the ones place. So this ends up giving us the same exact value as what we had before. Okay, so what do we have to keep track of? We need to keep track of repeatedly dividing by 2 until we get down to 0. We need the whole number part of that division, and we need the remainder from that division. So to do this in Python, let's write a function. And this time, rather than putting the 2 on there, this is one that we're going to want to keep. This method, we're going to keep it. So let's just call it decimal to binary. So dec to ben. Again, we have the parameter that we're going to call number. It's going to do the same thing, converting a positive integer to a corresponding binary string. We start off with the empty binary string. And now we are going to have this loop that is this while loop in this case, because now we have a condition. We don't know going in how many times this is going to be carried out. We don't calculate ahead of time how many times this is going to be carried out. All we care about is that the input value is greater than 0, and that's what it would take to be a positive integer. We would also later do some error handling to add in extra tests to make sure that the user has given us the appropriate kinds of values. Is it really an integer that they've given us? Right now it's going to be positive. We're going to extend this so that it works for negative numbers as well. But so long as this number is positive, we're going to want to continue the steps of what happened, what we just said. We're going to divide by 2, and what do we want? We want the whole number portion, and we want the remainder. Now, I'm going to skip over the loop for just a second, because just as before, at the end of it, we're going to return this binary string. But what we need to do is keep track of what we have created. Are we going to put in the 0, or are we going to put in a 1 in that particular place? So we need to look at the remainder, and we need to look at the integer value that follows from the division. And so what you get to do is determine what goes in this missing loop, remembering that we have a modulus operator, the percent symbol, that gives back the remainder after division, and we have the integer division operator, that's the 2 bars, that will give the integer portion of division. So if we just use a single division bar, then we just get regular float division, but if we use the 2 bars, we get the integer division. So we want to think about how to do what we just did in the example, keeping track of the integer part and keeping track of the remainder. And the remainder is the part we need to put in place, and it needs to go, or ultimately, it needs to be read backward from the way that they were created. We don't want to use any special tools, any kind of string operations, or do anything like that. So you also will want to think about how can you record these values in the opposite direction from the way that they are calculated. So rather than putting something at the end of the string when you get a new value, where might you want to put it in order for ultimately it to be recorded in reverse order? Okay, so this second method, why it works is a mathematical direction that we're not going to go in right now. You can try it with different examples and convince yourself, though, that it does, in fact, work. And we'll come back around later to how do we know that an algorithm does what we said that it does, and how do we prove that the algorithm is actually correct. And so we'll come back to this method later on. Okay, now we want to go the other direction. We want to start with the binary string and convert it into its corresponding number. So in this case, we'll start with a shorter binary string, just 1101. We already know what that number is. We can count that up. We can count on our hands if we like, and we can calculate what this value is. But the way we had described it before by hand was we started on the right-hand side with, okay, there's a 1 in there, there's not a 2, there is a 4, there is an 8, and so we know what this value is. But we want to do this in a left to right way, in the way that Python would read the string rather than right to left, just because we want to be able to think in a Pythonic way rather than necessarily the way we've been doing this ourselves. Okay, so what we need to do if we're going to work left to right is we need to know the value of each of these positions. And then if there's a 1 in there, then we're going to add in that value. And if there's a 0, we're not going to add in that corresponding power of 2. So when we look at the leftmost bit, we say, okay, what power is this? Well, there are 4 values here in the string. But remembering that as a binary number, the rightmost is 2 to the 0th power, then the first, second, and third. So this leftmost position is 2 to the 3rd power. And so that 3 is 1 less than the length of the string. It's always going to be 1 less than the length of the string. And as we go then left to right, the leftmost was the 3rd power, then the 2nd power, then the 1st power, then the 0th power. So the leftmost power is 1 less than the length of the string, and the powers are decreasing by 1 for each bit that follows. If there's a 1, we're going to add that value to the total, and if there's a 0, we're not going to add that value to the total. So this describes the steps, the idea of the function that would be able to convert from binary to decimal. And so let's again have a binary to decimal calculation that takes as input now a binary string. Again, we're ultimately going to have some error handling to be able to check to see whether the user really did give us a string and whether the string is actually a binary string. But that will come later. We do want our docstring in place that just describes very simply what this function's main task is. It doesn't go into the details of how that process takes place. The docstring doesn't need to tell an ultimate user how it does the thing. It needs to tell the user what it does. Okay, so in this case, we're trying to build up a decimal value. So we're going to start off with a number at 0 and then add to it as appropriate. We said the biggest power, the leftmost power, is the length of that string minus 1. And so we want to look at all the numbers from 0, all the powers from 0 up to that biggest possible power, except we don't want to go in the order from 0 up to those. We want to work our way down. And so there's a couple of ways we could do that, but in this particular case, we say let's go for I in range to power plus 1. Remember, the range is going to go from 0 up to, but not including that value that we give it. If we just give one number, it will start at 0 and go up to, but not including power plus 1. All right, so what do we need to do? Well, we need to have our power work its way down. So since power starts off as the biggest possible thing when we are at index 0, we will have power minus I is the meaning of that position. Power minus 0, that's the 2 to the power value at the left. We go to the next entry, the power is going to have decreased by 1. We go to the one after that, it will decrease by 2 and 3 and so on. Okay, now the reason we didn't change the order of the range here, we went in order, is because we also care about which bit we are on. We need to know from that binary string we're on bit index 0, bit index 1, bit index 2, and so on. But remember, the binary string is a string, and so to treat those zeros and ones as numbers, we need to convert those using the int function. So what do we have here? We have the number is going to be updated for every one of these 2 to the appropriate power times whatever value is in there. If the value in there is a 0, that's fine, and we just don't update the number. We just add 0. I guess we do update it officially in the way Python works, but we just add 0 to the value so it doesn't change the value. If the bit is a 1, then we are adding in that appropriate power. And when we get to the end of this, the last one will be power minus I, but I at that point will be the last value in the range, so it will be power minus power, and this will correspond to the ones place, 2 to the 0th power times whatever that bit is. If it's a 1, we're adding a 1. If it's a 0, we're not adding anything. So this calculation will work from left to right instead of from right to left in terms of calculating the numerical value of that binary string. It does require that we have the whole string so that we can find its length, but we as people don't have to worry about that, and we don't have to work from right to left. The idea of the loop works from left to right, decreasing the power as needed as we go. And then at the end, we return the number, and because this is all integer calculations, we have an integer at the end, and so we have created the thing that we are trying to create. Right, so we had the binary string, and we have this corresponding positive integer at this point because all the pieces are positive. All right, so that code, you can test that, you can try it, you can see whether your converter in the other direction is working by applying one and then applying the other. Do you get back to the same position? If you convert decimal to binary and then the binary back to decimal, you should end up back where you started if all the pieces are working correctly. If you end up someplace else, then something's not right because a number only has a single binary, a positive integer has a single binary representation, and a single binary representation corresponds to exactly one integer. So these things match up exactly. If you go one direction and then the other direction, you better get back to where you started. All right, so now let's look at another approach to do the same thing. Again, we are converting a binary string to a corresponding positive integer. Starting off the same way, the number is 0. So far, nothing new. But now, rather than doing this by index, let's do our loop in the Pythonic way. Let's loop by value instead of looping by position. So one way of looping with the for loop is loop by index, the other is loop by value. So now let's read our string. It's a bit by bit, it's going to be zeros or ones, and let's loop by value and determine what happens to number. Do we update the number? Do we not update the number? And what does this do in terms of which power are we using? What is happening at that point? So what's happening as we're going from left to right? We said earlier that the power is decreasing by 1 at each step, and the bit is a 0 or a 1. Now right now, again, it's still a string, just like it was in the previous method. So we're going to need to convert that to do calculations, to do numerical calculations with that. But the difference is going to be what goes in this particular loop, right? We know what we need it to do. We need the value and whether to count that position. And then we need the power to decrease as we read the string. And then again, just like in the previous case, at the end, we're going to return the number. And this will again be a positive integer that corresponds to that binary string. Okay, So you get an opportunity to fill in a couple of lines of missing code here to determine what the value is. Does it get counted? Does it get included in the total? Does number get changed? And we need the power to keep decreasing as we read through the string. At the end of the string, that power gets down to 0, and which corresponds to the ones position. Okay, so there are other methods for doing conversions. We can do these in different ways and think about them in a variety of ways. Python does give us some built-ins to convert decimal integers into other bases, but we don't want to use any of those at this point. But there is a built-in function to convert a number, let's say it's called value, to convert it to a binary string. You can experiment just to see what it does. It's not exactly the binary strings we have. There's some extra information that comes along with this string using this particular function. There's one that will convert to an octal string. Remember, octal is base 8. And there's one, a function hex, that will convert to hexadecimal. So you can experiment with these in idle, but let's not use them yet to do anything. You'll see that each of these functions yields a string that has 2 leading characters. And the 2 leading characters depend on which conversion we're doing. So you can look at one of these values and know, oh, this was our conversion to binary, or a conversion to base 8, or a conversion to base 16. Because you can't always tell from the symbols that show up which base something was in. If something is 1010, well, that could be in any of these bases. That's a valid number in any of these bases, but it's a very different number in the different bases. And so the strings in these built-in functions add some extra information so you know which base that this is in. All right, now, again, these functions can be really useful after we understand how they work, but right now we want to do these conversions, do these calculations from first principles, and that's what our functions that we talked about earlier, the ones we built, that's what they do. From how would you do this as a person to how do you then translate that into a way for the computer to do the calculation so that we more fully understand what the calculations are. And then as we add extra things to our toolbox, then we can start to use other built-in functions to do some of those pieces. Or again, now that we have functions that will do those exact same things, we can utilize our own functions in more complex scenarios. Okay, so as usual, feel free to ask questions in the comments, by email, or on Discord. And have a great day.